Okay, so we're going to pick up where we left off. We went ahead and found that for the second graph, when x is -2, y is 1/16, -1 is 1/8, 0 is 1/4, 1 is half, and 2 is 1. We're going to go ahead and graph this. I'm going to zoom in just a little. Whoa. And when x is 0, we're at a 4. So that'd be right about here. At 1, we're at a half. At 2, we're at 1. At -1, we're at 1/8. So that's down there. And at -2, we're at a 16th down there. We go ahead and draw our graph in. And we get our curve like that. Remember, our line will never cross the 0 axis. We're never going to cross that. Alright, so now we're going to go ahead and do the third line. Our third line, erase this work, is y equals -1/4 times 2 to the x power. So the only difference between these lines, our parent line, this was our parent line, was 2 to the x power. Then we had 2 to the x power, but we're timesing it by 1/4 to find out what that would do. And now this one is -1/4. So we're going to see how this affects our lines on each one. Here, when I put 0 in for my exponent here, I'd have 2 to the 0 power is 1. So this would be -1/4. When I put 1 in for my exponent, 2 times 1, or 2 to the first power is 2. 2 times -1/4 is -1/2. And when I put the exponent of 2 in, 2 to the second power is 4. 4 times -1/4 is -1. We work backwards to the -1. I'm going to show the work down here. This would have been -1/4 times, and 2 to the -1 becomes 1 over 2 to the first power. That would equal -1/8. And like you're probably able to guess, if I did 2 to the -2nd power, that becomes the reciprocal, so 1 over 2 to the 2nd power. 2 to the 2nd power is 4, so we'd get -1 over 16. When we graph this, 0, it's a -1/4. At 1, it's a -1/2. On 2, it's a -1. At -1, we're at -1/8. And at -2, -16. Okay, so there's our graph. This one that we just did, that is the one that we said we're going to work on tomorrow. That is going to be the decay, because it's going down. So when we look at today, though, this is comparing to the parent function. Our parent line was our purple line right here. How we compare these. When I compare these two, when I compare y equals 1/4 times 2 to the x power, exponent, we're going to say, if I look at the two lines, notice my parent function, how it went in this one. It did the exact same thing, it just kind of went out. We call that a shrink. So this line, y equals 1/4 times 2 to the x. When we compare it, we're going to say it had a vertical shrink. And the way we remember vertical shrink is because it kind of went farther out. Look at this blue. It followed my parent line, but it went farther out. It's like if I'm standing up, but I slouch down, I'm going to stretch out. The other possibility we have is something called, we're not seeing it here, but I'll do one on our homework today, is called a vertical stretch. I'm just going to write that down, and then I'll erase it. We could have a vertical stretch. If I had a vertical stretch, I'm going to draw it here in red, vertical stretch would follow my parent line, but it would go inside of it. It's like it's stretching it up. It's becoming thinner. It's getting shorter in the width, so it's going to be going up more. I will do one of those on our homework. I'll show you an example on homework today. If I look at my blue line, though, I shouldn't have that in there. For this last line, y equals negative 1/4 times 2 to the x power. That followed my parent function almost the same, but it was reversed. It was a decay. So first, we call that a reflection. We call it a reflection. But if I compare it once again to this parent, it's not only a reflection, because now it's going decaying instead of going up, but it's also like the second one that shrunk, because it went out wider. So when I look at this one, it went the opposite and it went wider. So we give it two names. It's a reflection shrink. If it would have just matched up with this parent function perfect, if it would have matched up with it perfect, it would have just been a reflection. But since it did both, it was a reflection shrink. So on today's homework, I'm going to write this down. Possible answers. Our possible answers can be a vertical stretch, vertical shrink, and a vertical reflection. And the special thing about that vertical stretch or reflection is you can combine it with the other two. You could say it's just a reflection, or you could say it's a vertical reflection stretch, or a vertical reflection shrink. Nope, I put shrink. Real quick, I'm going to draw a picture to kind of show you each one of those. So here's my graph. That's a horrible one. And we'll say this is my parent line. That's my parent. So blue is parent. So when I compare to that, let's do it in purple. The vertical stretch will be following that, but it's on the inside. Stretch. It became thinner. Shrink. Is the one that kind of became wider. It shrunk how steep our line is. And then our last one is a reflection. it reflected our parent line. Okay, I want to go up to this one. Okay, we skipped this one in class. Now, we have y equals 4/3 to the x exponent. So, to do this, remember this would end up kind of simplifying to 4x over 3x because of what we learned. We have to put the exponent to both. So when the exponent is 0, well, 4 to the 0 power is 1, 3 to the 0 power is 1. Remember in class, I think Grace had pointed out that we knew when we didn't have the a in our equation that it would be 1. Now, if I put 1 in for my exponent, I'm going to do number 1 over here. That means I'd have 4 to the first power, 3 to the first power. That would be 4/3. So this would be 4/3. Or you could think of that as 1.3. When I do the next one, 4 to the second power, 3 to the second power. That's 16 over 9. Or when we divide that, I'll make sure I tell you the decimal right. That's like 1.7 continuous. Just so I have something to base off. When I go this way to the negative 1, well, remember, if I have 4 to the negative 1 and 3 to the negative 1, we know the negative exponents means to flip them. So now I have 3/4, which is, or 3 to the first power of 4, so it's 3/4, and that's like 0.75. To the negative 2, so 4 to the negative 2, 3 to the negative 2, means to flip these first. 3 squared, 4 squared is 9/16. And 9 divided by 16 is 0.5625. Even though we're still as a fraction. And then we graph it. Okay, to graph it, I'm still just going to assume everything is 1. My scale is just 1. So, 0 and 1. And then when I did go over 1 into 4/3, we said 4/3 is 1.3. So I think it'd be like something around here. And then I have, that was a little high. Let's say 1.3. And then when I was at 2 is 16/19, which is almost 2, so it's right in here. Going backwards, negative 1 we said was 3/4. And negative 2 is 9/16, which is about halfway. I draw this in. Our line would look like that. Okay. Going down to our last two problems. Exponential growth model. Okay, so where a, or we have this equation, sorry. Y equals a times 1 plus r in parentheses t. This is still equaling our y times ab to the exponent x. The only thing is, instead of b, they're saying 1 plus r, and r is standing for our rate. The reason it's 1 is 100%. So this is saying, like, if I'm talking about in my bank how much money I'm making, well, when I find my interest, I don't just take, let's say I get a 10% interest, I don't just have $100 in there, they give me 10%, so they only give me $10. Well, no, I'd have my 100%, I'd have my $100 plus that 10%, so plus $10, that would mean I'd have $110. So, I'd have 1 plus r, and then t is what our x is, and t is just going to stand for time. How long are we having in this? banks actually use this. This is the formula they use. Now this says one computer industry expert reported that there are about 600 million computers in the use worldwide in 2001, and the number was increasing at a rate of about 10%. Write a function that models the number of computers in use over time. Okay, I'm going to zoom out just a little to get all this. So for number one, our function, we're going to say y equals a1 plus r over t. And we're going to fill these in. Y equals a is our initial amount. Our initial amount was 600 million. So I'm just going to say 600. And remember, it's in millions. Okay. In parentheses, we still have 1, and that 1 is representing 100%. So 100% of the 600 million computers. Plus the rate. Our rate was 10%. So make sure you write as a decimal. Have to write it as a decimal. So this would be 0.1. And then in our time is going to be t. This is your answer for the first one. The function is y equals 600 times 1 plus 0.1 t. Number 2, it says, use the function to predict the number of computers used worldwide in 2009. Okay, y equals 600, 1 plus 0.1, and in time, well, we're in 2009. 2009 minus 2001 is 8 years. So our exponent is 8. This would simplify to 600 times 1.1 to the 8th power. And if I was to bring up my calculator, 1.1 to the 8th power is 2.1435 and so on. And I'm going to times that by 600. I'm going to get roughly 1286. And can we have a decimal? Can we have a 0.15 of a computer? No, so I'm just going to round it down. So I would say there's roughly 1,286 million computers. Alright, then our last question, and then I'll look at a little homework with you. Compound interest. Interest on an investment in the previously earned interest use exponential growth model. This is what I was saying that banks will use a lot. So they still use this equation. Remember, this is the same equation that I just said as this one. The only difference is they break the b up into 1 plus the rate over time. B is like our slope. This is just going to be 1, and that stands for 100%, because 100% as a decimal is just 1, and then our rate. So you put $500 in a savings. So that's my initial investment. So I'm going to say y equals 500 into a savings account that earns 5% annual interest compounded yearly. That's how we know we're using this compounded interest. That's how we're using this little equation. So 5%. I'm going to come back in here and say, okay, 1 stands for 100%. So when they give me my money, they tell me how much money I have. They're going to say, well, you have 100% of your $5 plus 5%. 5% as a decimal is 0.05. And it'd be over t for time. This one is telling me, or not t over time, it'd be our exponent of t. This is saying you do not make any deposits or withdrawals. How much will your investment be in 4 years? So my time was to the 4th power. Once again, what this is telling me is I initially put in $500. I have to take it times 1 because I get 100% of that $500. When I take it out, I have 100% of that $500. But along with that 100%, I also get 5%. And we do it to the 4th power because every year that investment adds to it. So I had $500 plus 5%. All that money, that new total, the second year, is that new total times another 5%. So when we do this work, we first simplify 500 times 1.05 to the 4th and bring up my calculator. Where did it go? 1.05 to the 4th power is 1.21550625. We could round to the nearest 10th or 100th, or I'm just going to leave this in here right now. And I'm just going to say times. So I'm taking that whole number times 500. And $607.75. So I'd get 607.75. So if I initially put in $500 into a bank where I was having a compounded interest at 5%, in 4 years, when I took that money out, instead of $500, I'd have $607.75. Okay, homework. So I'm going to look at your homework real quick with you. Here's your worksheet. Write the rule. I can get to this. Okay, so write the rule for the function. Remember, to do so, what is this going up by? It's going up by 1. Here, if that's hard to tell because it's a fraction, I go to the whole numbers. 1 times 11. 11 times 11 is 121. Because my y is multiplying, that's how we know we're doing our exponential growth. I'm looking for the equation y equals a times b to the x power. A is our y-intercept, so we look for when x is 0. So I'd say y equals, and if it's 1, we've already seen this in examples, we do not have to put it. I don't have to put 1 times something. So if I want to, I can say, I'm going to write down here that a equaled 1. And now I have to find b. Well, b is my slope. I was multiplying by 11, and my x is going up by 1, so it's 11 over 1, or we would just say 11. Our power to the exponent is still x. Our equation, our rule for this function is y equals 11 to the x power. Okay? So now if I said on this table, what is the 5th power, or what is the y coordinate when I go to the 5th, when x equals 5? I would do 11 to the 5th power, and that would give me y. On 3 through through, I think just 8. Right. 3 through 8. Identifying your domain and your range. So you're going to make a table. Graph the function. To do this, I would go ahead and say x, y. When I only have to do a couple. I do a negative to get on one side. I do 0, and I would do 1. So when x is a negative 1, I'd have 12 to the negative 1 power. That'd be 1/12. When x is 0, 12 to the 0 power is 1. And when x is to the first power, 12 to the first power is 12. We graph this one. I'm at 0, 1. I'll put that dot here. At 1/12, here's 1, 8, 10, so it looks like here. And negative 1 to the negative 12, somewhere around there. Draw your line in. There's my graph. Then you have to define your domain. And I will say my domain is all reals. All real numbers. Another way, instead of writing all that out, is it looks like that. It's like 2 R's, all real numbers. My range on this one, y is greater than 0. Okay. Everything here has to be greater than 0. Okay, on the last part I'm going to help you with, on number 9. So I'm going to make a table again, same thing, x, y. I'm going to say negative 1, 0, and 1. I always like doing the 0 first. So when x is 0, 6 to the 0 power is 1, and 1 times 2 is 2. 6 to the first power is 6. 6 times 2 is 12. Go to the negative. 6 to the negative power is like 1/6. And times 2 would give me 1/3. 2 6, I simplified to 1/3. I then will go ahead and graph this. Okay, so at 0, 2, 1 and 12, and negative 1, and it's 1/3. So there's 1, there's about 1/3. So there's my line. Well, on this question it said, graph the function, compare it with the graph of y equals 6 to the x power. Well, 6 to the x power. That is my parent for all of these. It's my parent. So I'm going to kind of cheat over here, and I'm going to say this. Oh, sorry, I'm a bad line. So this is going to be y equals 6 to the x power. I'm going to make that table because I'm going to use it on all 3 of these. So if x is negative 1, 0, 1. When x is 0, 6 to the 0 power is 1. When x is 1, 6 to the first power is 6. And to the negative 1, it is 1/6. I would graph that on all these. So my parent function is 0, 1. 1/6. Negative 1, 1/6. Draw my line in. That blue one is my parent function. So, how does a line compare? How does my purple line compare with 6 to the x power? I would go ahead and say, since the purple one is skinnier, it's a steeper line, That is our vertical stretch. Remember, vertical stretch means it is skinnier. It goes inside the parent function. The other one is vertical shrink. That's like the line it kind of sag down. It's going to hang outside. That is the shrink. I'm going to erase that. And then remember, the reflection would have been like that if it was just the opposite. So, on all three of these, I've actually done number 1 for you. On number 10 and 11, you're going to want to graph this line. I would graph it in one color, show what it would be, and then go ahead and make your table for each one of these. So for this one, x, y. Make x negative 1, 0, and 1. Put in this function to get your y. Come over here, same thing, x, y, negative 1, 0, and 1. Put in this function to get my answer over here. Okay, I feel like you should be able to do the rest. Let me know if you have questions.